Hey, welcome. Today we're jumping into the world of statistics. And look, I get it. For a lot of us, that word brings back memories of a, let's say, very dry math class. But this is going to be different, I promise. We're going to treat statistics like what it really is, an amazing toolkit for making sense of a really complicated world. It's how we find the real patterns, the signal, that's so often hiding in all the random noise.
Okay, just think about this for a second. It honestly sounds a little bit like a magic trick, right? How on earth can you figure out what millions and millions of people are going to do just by asking a tiny fraction of them, like 1,000 people? Well, this is one of the coolest puzzles that statistics helps us solve. It's all about understanding how a small but very carefully chosen sample can tell you a surprisingly accurate story about the whole group.
All right, so let's start at the beginning. What is statistics really? Because it's so much more than just crunching numbers. It's a structured way of thinking. It's a whole framework for turning messy, real-world data into clear answers. And you see it everywhere. From business and biology to, computer science and psychology, it's essential.
And that is the absolute core of it. It's a discipline of critical thinking, plain and simple. It gives us the tools to look at some headline about a new study or a political poll or a company's sales figures and ask the right questions. Like, is this conclusion legit, or am I being misled here? It's really all about how to weigh the evidence properly.
Everything in statistics, and I mean everything, starts with the data. If your data is flawed from the get-go, then your conclusions are going to be flawed too. It doesn't matter how fancy your analysis is. This first step, gathering good, solid evidence, is absolutely the most important part of the entire process.
And this right here, this is the secret sauce. It's called random sampling. This is the big idea that makes a poll of 1,000 people actually work for an entire country. By giving every single person in the population an equal, random shot of being picked, we end up with a sample that acts like a perfect, unbiased, miniature version of the whole group. This is the bedrock of any credible research.
But the thing is, the stakes for getting this right are unbelievably high. It sounds simple, right? Just pick people at random. But messing up your random sampling can completely destroy your results. In fact, one of the most famous examples of this led to, one of the biggest polling blunders in modern history.
So this quote is talking about the 1936 Literary Digest poll. They were a huge magazine, and they predicted a massive, landslide victory for Alf Landon over Franklin D. Roosevelt. The problem? They were completely, spectacularly wrong. And why? Because their sample wasn't random at all. They polled people from telephone directories and car registrations. And back in 1936, that meant they were mostly sampling wealthier folks, which created this incredibly biased picture and totally missed Roosevelt's actual supporters. Okay, so let's say we've done it right. We've gathered good, random data. What's next? Well, our next job is to describe what we've actually found. We need a way to take all those individual numbers and summarize them into a clear, understandable picture that tells a story.
And what's amazing is that so often, data out in the real world follows this beautiful, incredibly useful pattern. We're talking about everything from people's heights to test scores. You see this shape pop up over and over again. Data points just tend to bunch up right in the middle, around the average, and then they get less and less common the further away you get from the center. Now, what makes this bell curve shape so powerful is just how predictable it is. If your data follows this pattern, we automatically know that about 68% of all your data points are going to fall within one step of the average. Stretch that out to 2 steps, and you've captured about 95% of everybody. And almost everything, a whopping 99.7%, is going to be within 3 steps. It's this fantastic rule of thumb for understanding the spread of your data with just a glance.
So those steps we just talked about, how do we actually measure them? Well, we use a tool called the standard deviation. It's really just a single number that tells us the typical distance that any data point is from the average. Think of it as our yardstick for the bell curve. If you have a small standard deviation, it means all the data is packed really tightly together. A big one means it's all much more spread out.
Okay, so we can gather data and we can describe it. But the real power of statistics, where it gets really interesting, is when we use that data to make decisions. And the process we use for this, it's actually a lot like a courtroom trial.
So let's picture a scenario. A company spends a ton of money on a new training program, and after it's over, hey, performance seems to be up. But here's the big question. Was that improvement a real effect from the training, or was it just, random luck? The kind of little fluctuation you'd expect to see anyway. We need a verdict.
So, In our courtroom of data, we always start by assuming the defendant is innocent. This is what we call the null hypothesis. We start with the assumption that our training program had zero effect, nothing. Our data is the evidence we're going to present to try and prove that assumption wrong. It's a really skeptical starting point, and that's exactly what makes it so powerful.
And the trial itself follows these 4 very clear steps. First, we state the charge. That's our null hypothesis. Second, we set the burden of proof. Basically, how strong does our evidence have to be to get a guilty verdict? Third, we present that evidence, our statistic that we calculated from the data. And finally, step 4, we make a decision. We deliver the verdict.
All right, so let's look at the numbers for our training program example. The evidence we actually collected from our data, our observed statistic, is 2.38. Now, the burden of proof, the bar we set before the trial even started, was 2.132. So you can see it right there. Our evidence of 2.38 has cleared the bar we set. And so, we have our verdict. Because our evidence, that 2.38, surpassed the burden of proof we required, 2.132, we reject the null hypothesis. We have enough evidence to call our results statistically significant. And all that really means in plain English is that it's super unlikely this improvement we saw was just due to random chance. It looks like the training program actually worked.
But, and this is a big but, just like in a real courtroom, our verdicts aren't perfect. We can make 2 different kinds of mistakes. A type 1 error is a false alarm. It's like convicting an innocent person. We say the training worked when it really didn't. A type 2 error is a missed effect. That's like letting a guilty person go free. We say the training did nothing when it actually did have an effect. And there's always this tension, this trade-off between those 2 errors.
So this brings us to the most important idea of all. We've gone from gathering data to describing it to putting it on trial. What's the one single idea that ties all of this together? What's the point of the whole shebang?
This quote, "This gets right to the heart of everything we've talked about." That phrase, sampling error, that's just a fancy technical term for the random noise we keep mentioning. It's that natural, unavoidable difference you always get between your small sample and the entire population. So hypothesis tests, the whole courtroom trial, they exist for one reason and one reason only, to help us figure out if our result is bigger than that expected noise.
And that's it. That's the ballgame. The entire massive field of statistics really boils down to this one beautiful, powerful question. Is the pattern I'm seeing in my data a real, meaningful signal, or is it just the random, meaningless chatter of noise that you always get from taking a sample? Every single tool we've discussed today is designed to help us answer that one question.
So from now on, the next time you see a headline about a new medical study or a business report or some political poll, you have the mental framework to ask the single most important question you can ask. Is what they found a true signal that we should all pay attention to, or could it just be the random noise in the data? Honestly, learning to see the difference is a superpower.